Hey everybody, looks like we're almost finished with the semester. Yeah, week 8, so there's tonight and Thursday for class. There's a final exam, but I think most everybody's already taken that. Saw some great answers on the essay part. I still have to look back over the multiple choice part because I didn't write that test, so sometimes I often find that I don't necessarily agree with the answers or what the answer key says. So I always look back over the multiple choice parts, and I still have to do that. And I saw some great answers on the essay portion. The final project's due this week. Remember, just share the PowerPoint you made with it in the discussion board so your classmates can see what it's about, maybe a quick paragraph or so write up or something like that. And then submit both the PowerPoint and the written essay format to me. And that should finish up most of our work. And like we talked about last week, this class is informatics. That's just general computing stuff. There's a lot to cover. And we covered a lot of information, but there's some things that didn't get covered. And I wanted to talk a little bit about some of those this week. In particular, the one for tonight, it's something that's barely going to be mentioned. So unlike some of the other things in here where we did just a quick pass at it, well, it's still going to be a quick pass, but I wanted to try to be a little bit detailed, not getting super detailed, because tonight's topics, we're going to talk a little bit about graphics. That's a big part of IT, right? Conveying information. And the very first words I have in my notes here are that classic saying, a picture's worth 1,000 words. I think everybody's heard that before, right? Humans are a visual species. We like to see imagery instead of read words on a page. So graphics are an important thing, but it wasn't really on the list of things to cover. And you'll find that in most of your classes, it's kind of skimmed over, if mentioned at all, right? Most of your classes, it's gonna be like, okay, graphics are something that exists, and that's about all you'll hear on them. So I wanted to talk about some of the, at least a quick covering on some of the common formats. 4 or 5, yeah, the 5 most common, and then a quick pass talking about a little bit about 3D graphics, and talk a little bit about those, and then we'll kind of see some application of it. Just a quick introduction to it. Obviously, it gets a little complicated, and really for what we're going to look at in the active part there at the end, it's just a time thing. We'll look at some of the basic concepts, but a lot more time than we'll have tonight is required to put really nice animations together. I wanted to point out the basic concepts of it. We'll see that in a few moments. So first off, some terminology and concepts and things like that. Yeah, then we'll look at some basic 3D graphic stuff and do a quick pass at animating 3D animations and 2D animations. I wanted to end with the 2D animations because that's what we would need to put in, like, say, a PowerPoint. And I know several people in the class have expressed interest in, like, security degrees. So that's something you're going to want to have, is when you explain to people what happened to where their security was breached or what could happen, you're going to want a nice 2D animation to put in the PowerPoint. So I wanted to make sure and end on that one, because that's something that might be a little bit more useful to throw together nice animations for a PowerPoint or something. But talking about this a little, so that classic saying, a picture's worth 1,000 words. It's very true. Humans are a very visual species. We can understand stuff by looking at imagery and things. So it helps to convey information. So especially on, like, that point I just made about, like, conveying information about a security breach that happened or a security breach that could happen to a client, they're not going to understand all the technical jargon, right? They might be somebody that studied business, so they have very limited knowledge of the technical aspects of security. So if you just listed out a bunch of technical aspects, they're not going to follow along. So you want to put stuff like that in a picture, and it helps helps it to make a lot more sense. So humans are very visual, and people want that. People want imagery, not descriptions. So storing image data in a binary format, in binary encoding, is obviously a little bit more tricky than alphanumeric coding, right? For our basic characters written language, which you all will see this in your SDev 120 class, we can just say things like, okay, a capital A, we're going to represent that with the number 65. A capital B will represent that with the number 66. And just go all the way through all of our symbols like that. You'll see that in your SDev 120 class. Even do some translating from binary encoding into a decimal number, into a word, and get some messages going. That's homework assignments in that particular class. So that's very straightforward, right? We just correspond we say this symbol is represented by this number. Just basic alphanumeric encoding. To store image data, pictures where we have colors and locations of things is a little trickier. But people are definitely creative and persistent and have come up with a lot of solutions. So let's just quickly look at some of the most popular ones, the most common ones that we'll see. So that's tonight's topic, is graphics, which again, in most of your courses is going to be skimmed over. At most it's going to be like, yeah, graphics are something that exists, but we've got lots of other stuff to talk about. So I wanted to make sure and cover it here where there's a night to cover the other stuff. So our first one, most basic one, is a bitmap. Usually, like our file extensions, is going to be a .bmp file. And this is just the most basic image data. This is probably what you would come up with on your own without spending a lot of time thinking about it. And it's a collection of instructions on what each pixel should be. Collection of instructions. Whoops, broke my chalk. A collection of instructions about each pixel. So for example, to kind of put this in an image, I'm just going to draw a big 8x8 grid here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That turned into a piece of chalk pretty quick, but sort of a grid of pixels. And we'll just set up some instructions about what each pixel is going to be. Our basic, well, like a map. That's a good way to think about it. So over here, we'll say, let's make this pixel yellow and this pixel yellow. And then the next row down, I'll make some more pixels yellow here. A couple more yellows. So we got a bunch of yellow pixels over here. Then down along the bottom, let's do all these pixels green. So I'll just write a G in there to represent that here. Obviously, there's a little bit more when we get into the encoding, but just kind of covering the basic idea here. So a whole bunch of G's down here to represent green. Maybe some brown. BRW. A couple brown ones and some more green ones over here. And then, yeah, for the rest of these, I'll just make them all blue. I'll write a B for that. A whole bunch of blues and all those other ones. So that every single pixel is organized, set up nicely, and then we have data about it. So like these pixels are going to be yellow, And there's some other colors. Hopefully the colors are somewhat showing through here. Then all these pixels are green. All these pixels are green. I put some more green pixels here. I don't have a brown, so I'm going to make this purple. That's supposed to be brown, but I didn't have a brown one. But those pixels would be brown. Then I don't think this one's going to show up on the screen at all. Then all these other pixels would be blue. And we build up an image by defining what each pixel is going to be. That's just the most basic type of data. It's called a bitmap. Obviously, there are some drawbacks. There's a number of limitations because, well, we have to define how much space a pixel is going to take up, right? Every one of our computers have, or our devices have different size pixels. The laptop here, my phone here. If one of y'all is watching this on a big desktop with a big, huge monitor, we have different pixels, right? So if we set up to look good on a small screen, it's going to look a little funny on a big screen. Or if we make it for a big screen and try to shrink it down, our pixel count's going to get off and it doesn't scale up or down real well. So we need some other formats to do that. But a bitmap is just our basic image data, just the basic starting point, and it still works in a lot of situations. So we do go ahead and stick with it. And this is sort of the basic image I was going to use this evening. Just supposed to look like a sun and a tree and some grass. So I'll keep referencing that. But I need to erase this to get ready for the next section. Is it okay if I go ahead and erase this? But very straightforward, probably what you first think of as far as storing pixel data or image data. Like, okay, we have a bunch of pixels. Let's just say what color each pixel is going to be until we have an entire picture drawn up there. Will I be able to fit all 5 here? I think I have to erase this too. So that's the first one, bitmaps. There's different amounts of writing on each one. So I have a new set of notes, so I don't know exactly how it's going to fit on the board either. But there are some drawbacks to that. We need something that can create that map. That way, that thing I talked about, it doesn't matter what size of screen we draw it on. If we want to open that picture on a big, huge desktop monitor or a phone, we can recreate that map. So the second one on my list here of very common ones is joint photographic experts group. Which normally we'll recognize those because they have the extension .jpeg. .jpg, or sometimes we'll see .jpeg, but we usually go ahead and call that a JPEG. And you'll see the name doesn't really describe what it is, like the bitmap. It was a map of every pixel on there. This one's named after the people that invented it. But the idea for this one is color data. I'm going to underword the word color. Color data is stored as and I'm getting ready to use a big math term here. Hopefully it's not going to scare anybody off. Color data is stored as a discrete cosine transform. So what that means, I'll put it in a picture here, is we're going to translate our data from a nice real world continuous signal into discrete values. We're going to break it up into separate individual distinct parts. So like instead of a smooth curve, a discrete would be like steps that kind of simulate that curve. Cosine is one of our main methods for describing a wave. And transform means we're going to put a whole bunch of them together. So the image I had in mind here is we might have something to represent a red. We're going to take everything about that image that is red and describe it as some sort of wave. And same thing for our other colors. Our green, maybe it's going to look something like that. And we'll end up with a wave describing all of our color data. Our blue data, maybe split that out really far. And I just made those up completely. Then maybe for the example, maybe some grayscale, how dark or light it is. And I'll just draw some random wave that's completely random, made up. Those don't necessarily represent anything. But they're just generic waves. But then we can put those waves together. And the idea behind that is kind of like where this wave drops low, it would cancel out some of the high from this wave. Or places where both waves would be high, they'd combine together and make a bigger high part or lower low part. So we combine all those waves. And in the end, we end up with some very, very complicated looking wave, which again, I'm just making this up here. It might look something like this. So we end up with this big, complicated looking wave. And then that is our JPEG image, our JPEG data. So glancing at that, depending on what you've seen before, that might remind you of like sound waves. However, it's not exactly stored like sound waves. Because remember, when we store sound waves into, well, this word here is the only one that we would have in common if we look at the big math terms. So a sound wave was going to look similar to that, but we can reproduce the sound wave, right? We store it as some sort of transform, and then we can reproduce that electrically. And that's not the case here, because we don't have everything necessary for an image. All we have is color data. So we could not use this to reproduce a light wave, per se, the same way we can reproduce a sound wave. They just happen to look similar, and I wanted to mention that to clear up any confusion. It's not the information about a light wave stored the same way we would store sound wave information. It is just the color data stripped down and put in this format. Yeah, it's just raw color data. Yeah, I had a feeling that one was going to take up the whole board. It's okay if I erase this for the next part. And I'm going to talk a little while I erase it. You can probably see a problem with both of those types. The order is going to matter a whole lot here, right? Because the opposite of a Fourier transform is a Fourier analysis. So once we get this, this is how we store the data, and then the computer has to break it back down into this in order to put the image together. That's a big continuous wave signal. So it obviously, the order is very important, right? the order that wave comes through is very important. And same thing with a bitmap. The sequence is going to be very important because we're just going to start at that top left bit and top left pixel and go across and then go down row by row by row. So the sequence that data comes in is very important. But, well, y'all are well aware of a little thing called the internet, right? It's very important to be able to transmit data. And the sequences can get messed up when we transmit stuff. You might remember TCP protocol. The main protocol by which we transmit data across the internet is we break it down into little pieces, we call them packets, and then send each packet individually across the network and reassemble it on the other side. So if we have something like bitmaps and JPEGs where the sequence that data goes in is very important, it could cause issues or at the very least slow transmission rates, because if something goes wrong, we need it in that particular sequence, right? So if we have, maybe like in a bitmap, if that bit right there gets messed up, our sequence is off, so we can't just retransmit that bit. We have to retransmit the sequence. And even worse on that waveform, if that's our data, because it's very important, the sequence and stuff, so we need some ways to transmit it better. And the first of those that is still commonly in use, again, there's lots and lots of these have been created, but the first one still commonly in use is graphics, interchange, formula. I had to look at my notes. I always forget what the F says. I always want to say format there, but for some reason it is formula. So I've forgotten it so many times that this might be a good little side step for introduction to IT type of course. Is I've forgotten that so many times that I just finally made a note to remember that I always forget that it stands for formula, not for format. So sometimes that can be handy when we don't remember exactly what it's going to stand for. Just remember that we're remembering it wrong or something. I found it to be very useful. Maybe that is something you could find useful. These will recognize by the extension .gif. Very common anymore. And really, what all this is it restricted the data being transmitted. Like, okay, the problem is we're losing data in transmission, so let's put some restrictions on so that we don't have as much to transmit. It's easier to make it easier to reassemble, basically. So it's a special type of bitmap. So we still have that pixel by pixel instruction on how to put them together. But so I'll say a special type of bitmap that defines its own color space. So that's the part I'm going to talk about. There's a little bit more that's starting to get advanced, and the reason that it's formula, not format here. But the basic idea is, well, if there's too much data to transmit, and if it gets messed up along the way, it gets hard to reassemble. So let's make that easier. So say we have all possible colors. So from this bubble of all possible colors, we're going to restrict that and just use these. Use these and only use these colors. And we'll send that data separately, what colors we're using, so that when it gets reassembled on the other side, there's not as much data to put back together. And there's some other stuff involved there too that gets very technical, but it still kind of follows this basic idea. We restrict our data. So instead of all possible data being sent, like, okay, there's 1, 2, 3, 4, 5, 6. There's 2 to the 24th possible colors. But we're going to restrict it so that at most we'll use 2 to the 7th colors, which that one I know, that's 256. 2 raised to the 24th power is a really big number. You can check it on the calculator, but it's probably, let's see if it's a calculator overflow. So 2 raised to the 24th power is that number. So there's a whole lot of possible colors. And that's just our most basic way of representing colors. That's representing RGB colors. We have other ways to represent colors in computers too, so there's actually a lot more than that. But just if we think of RGB colors and not even RGBA colors, which would have transparency included too, just RGB colors, there's 2 to the 24th that we can represent, which is way too many. It's hard to assemble that data on the other side, so we're just going to pick up to 256 of them. We're going to limit how many colors we're using in our image. And it makes it a lot easier to assemble on the other side. And then there's some technical stuff happening that follows that same idea for other things. But essentially, it's still a type of bitmap. And then we use that restricted data to define a set of instructions for pixel by pixel data. Kind of worked a little, but it is still a bitmap. We still have that sequence being very important. The order it comes, the order is very critical. Everything has to go together in pieces. Is it okay if I erase this for the next one? I'll pause for a second. And yeah, just restricted data is how we restrict our data to make it easier to assemble on the other side of the network after we transmit it. And that's the basic idea of GIFs. But it's still, some of those problems, like the sequences, the issues are still there. And a couple other things is nothing's perfect, right? And a couple other issues, but people were pretty quick to say, well, we can do better than that. In particular, we know, so by the late 80s, there were a lot of, through the 70s and early 80s, there were a lot of different protocols go back and forth because, well, we mentioned TCP briefly, and there's a lot of overhead involved in TCP. There's a lot of overhead involved in breaking our data up into separate chunks, sending those chunks separately, and then reassembling. But by the mid to late 80s, 1980s, computers could handle that overhead. It wasn't much of a problem. We didn't mind passing a little bit extra work onto them by then. So once they could handle it, we knew we were going to be using TCP protocol because it's, or TCP, to the P there stands for protocol. I always want to add that word at the end. We knew we were going to be using TCP to send the data. It's like, okay, we know how TCP works, so why don't we design image data around TCP? Because that's how it's going to be transferred. And that's where we got portable network graphics. So it's intended for speedy transfer. It's modeled after TCP protocol or to fit nicely into TCP protocol. So image data, and this is why I underlined that word earlier. I remember when we were talking about JPEGs, I underlined color. This time I'm going to underline image data. Not, so there's other stuff than, there's more than just the color involved there. But the image data is described in chunks, which are designed to be transferred into packets directly for TCP transmissions. And the chunks are labeled as either critical or ancillary. So that if there's network communication problems and you start to lose some chunks, the computer can decide which chunks are most important and which ones can be disregarded to get that transmission coming through clearly and quickly. Then pixels are grouped in layers which reference the chunks. So everything's split up into little pieces already. The way we originally stored our image is in little packets of data. So then when we go to transmit it, we can just transmit those packets. So to represent this, so like the first thing that comes in on the other side of the network, maybe there's a chunk of data for grayscale. And right at one end of that scale, we have black and the other end white, right? So it's really dark and then kind of gets lighter and lighter and brighter and darker sort of information. So we have one chunk of data just describing how bright the stuff should be. Then we'd have a lot more than this, but I'm just going to do a couple simple ones. We'd have a chunk of red data and a chunk of green data and a chunk of blue data. So we get a bunch of information about, a bunch of information comes in first, and then our layers start coming in. So there'll be a layer that, I guess another important one here is like with image data, we'll have the size and all sorts of other things coming in. We'll have all those chunks. So maybe first off, we get something that's a little circle. The pixels are set up so that we just have, which is back to a binary format. So kind of like a bitmap. I'll draw a small one. And then we can, since most of our data is separate, we can just do included or not included on these pixels. So we can say, include that pixel. So like, don't include that pixel, include that pixel, don't include that pixel, include that pixel, include everything in the next row. Then we can just split it back to a binary states of include or don't include that data and reference this stuff. So we'll have like a circle come in and kind of the same image I was doing earlier. So when that circle is going to be yellow in the final image. So yellow is an even mix of red and green. And then it's way over here on the white scale. Oh, I guess maybe one more down here. So along with the size data, we also have position data. And then there's another reference that says, okay, put this in some position over here. And then we'll have another layer come in. Our next layer, gonna have a bunch of background stuff. It's gonna have a circle missing where this is gonna fit in. And then I have some more stuff I'm gonna put here. Might remember that image I drew was kind of like a little tree. There's a chunk missing there. And we have this layer here that refers to the blue chunk of data. So we include these pixels and then reference the blue chunk. Then somewhere in the white scale, and then stick that somewhere in the position data where it'll load in place. And this one, I'll kind of separate some stuff. Then we'll have this chunk that has these pixels included, and that chunk's going to be green, have some position, white scale, and those arrows are already starting to be a mess. So I'm going to stop drawing all of them. Hopefully you got the point there. But that included, that layer of included pixels refers to green, gets positioned somewhere on the image. What's left? Then I guess we'll have some brown image, which again is a mix of red and green, just like yellow, with different ratios to be a brown image, and we'll position that. And everything's split up into little pieces already, into little packets of data. So when we want to transmit it, all those packets get transmitted separately, and every single one of them, the layers, the image data, or every chunk we're sending is also labeled as either critical or ancillary, so that if there's problems with the transmission, the receiving computer knows which ones are most important, which ones it can ignore, and which ones to really work with. So that's portable network graphics, or I forgot the little abbreviation, .png, which we typically pronounce as ping. So ping images, that's when you'll see a lot of. I forgot to include it in my notes. Transparency is a big issue too, right? We might not want to color every pixel. Maybe we're going to lay this pixel on top of a different, maybe we want to set our image on top of another image. So we need some transparency. So not all of our images formats can handle transparency. That was another problem with bitmaps and JPEGs. All that data is sequential. It all goes together in the right order. So it's all important. So we can't leave empty pixels. But with GIFs and pings, we can just say that some of our pixels are going to be left empty, and then have some transparency in the image as well. So those are very commonly transferred ones. The other problem that I mentioned with the bitmaps and JPEGs, right, if we, what size screen is it showing on? Do we want that image to be stretched out really big or squeezed down really small? And scaling can be a problem, because we still, even with the ping graphics, we still have pixel data, pixel by pixel data. So to address scaling, we have to do something different. Is it okay if I go ahead and erase this now? Hopefully that's making sense. Just a quick pass in the general idea of how we store this information. All right, everything we've seen so far, we're defining pixel by pixel data. Oh, I should write a word up here. These are what we call raster graphics, and that's pixel by pixel data. I'll put this up here and erase it last. Pixel by pixel data. So a whole lot of information, it doesn't really change. We kind of run into problems when we try to scale it up and down, because if we exceed a certain size, we have to stretch that out. So what was 1 pixel now has to take up 4 pixels, and it starts to get blurry. Or if we go the other way, what was 4 pixels now has to fit into 1 pixel. So we lose quality when we do that, if we make it bigger or smaller. So aside from raster graphics, I might as well put this label over here right next to it. The other big type is vector graphics. Math equations. So a vector, mathematically, you may not have encountered that in any of your math classes. A vector is a number with multiple components. So that if we wanted to draw a line, say, with a vector, we could do that with 2 parts to the number. We could say it's 3, I'll put inches long, and it curves at 30 degrees. Actually, I'm going to make that bigger. 23 inches long. That way I can try to do something roughly accurate here on the board. It's about 2 feet long, a little less than 2 feet long, and it's pointing at going off at 30 degrees. We represent that line with those 2 pieces of information. So maybe that's 23 inches, and it's pointing that it's going up at 30 degrees from our horizontal. So that's what a vector is. It's a number built up in more than one part. But a math thing, it's all mathematical. So instead of storing pixel by pixel data, we can store equations to represent that data. I'm going to erase this. That was just a quick example, sidestep into what a vector was. So values that contain more than one critical part to them, basically. So first one I want to talk about that we'll see a lot is scalable vector graphics. And these are 2D things. So image data is stored as points, lines, and curves on a Cartesian plane. So if you're not familiar with that one, Cartesian, Descartes, French philosopher come up with it. That's the one you've probably seen in your math class, where we have our x-axis and our y-axis, and we can describe all the points in between. So like up here, we might have a whole bunch of blue x, y points to fill up all that background space. And then somewhere over here, we have a yellow x squared plus y squared equals r squared. That's the equation for a circle if you haven't seen that. Then down here at the bottom, maybe some green y equals mx plus b, the equation for a line. There's several of those to get some ground going down there. And I guess going upward here, there's also a brown line with a y equals mx plus b. And we have that equation, obviously a different line once we start filling in the m's and b's and x's and y's. But a brown line going up and down to represent the trunk of a tree, and then another green x squared plus y squared equals r squared. So we have all of those equations for points, lines, and curves on a Cartesian plane, and we can put those together to make image data. And then we don't end up with that scaling problem, because what we stored is just an equation that describes it. So it doesn't matter if we put it on a really big screen or a really small screen, the computer's going to run that equation in live time at the end and just draw what those equations, display what those equations result as. So it scales up and down without losing any information. We're going to look at that in an example here in a moment. I want to do that one last, because this is how you would do a quick 2D animation to well, maybe not quick, because obviously the more time you put into an animation, the better it's going to be. But this is how we put together easy 2D animations to like put into a PowerPoint and express a point, express your topic clearly through image data to a customer. is, well, clients probably don't know all the technical terms if you're like talking about a security breach or something. So scalable vector graphics, just the stuff you learn in your basic algebra classes, elementary, intermediate, and college algebra, and then the first at least 1, 2, and 3 levels of calculus, just the basic XY Cartesian plane stuff. And we store those equations. But, well, before I erase this, y'all are probably aware that we can add another axis to this, right? And it's very common to do so. Usually then we have our X over here coming out, in and out of the board. We put our Y going off to the right, and our Z goes up, is sort of the standard format for it. But this stuff should translate very nicely into 3 dimensions as well. So that's the last one I wanted to talk about briefly. And there's a lot of types of them. So I was just going to give a general idea of how we do it and not get into a particular type yet. We might look at an example or 2 of them, but yeah, we'll just talk about the end result because they're all very similar. It's okay if I erase this. And this is our most popular 2D form of vector graphics so that we don't end up with scaling issues because everybody's going to be looking at our stuff on different screen sizes. So we want it to scale nicely. Oh, and while I'm talking about this, something you've probably heard, or at least vaguely, perhaps just noticed, that a lot of artists seem to use MacBooks. And you may have heard that, or use Macs. And you may have heard people say that about Macs. And this is where that is true, that any of the Mac OS operating systems are better for graphics, are better for 2D graphics. And what it has to do with, kind of like that pixel data, this time I'm going to draw the grids. So earlier when I did a picture, the pixel, we're using in between we're using the squares to represent the pixels. So on this grid, that's the line is the row of pixels. And then the square is the space between pixels, because we do have, right, they're not, in the real world, there is space between those pixels. And this is where MacBook, I always say MacBooks, but yeah, the desktop Macs as well, anything running a Mac OS system stands out here with 2D graphics, because on our Linux or Windows systems, in order to make things more efficient, it approximates it and rounds it to those lines. So if we try to draw a straight line, we might actually have points like this that are just a little bit wavy, or something colored. Hopefully this will stand up. So they pretty much, since we can't turn on the space in between the pixels to keep efficient, to make it more efficient, Windows and Linux just goes ahead and uses those numbers and rounds it to the pixel. But on a Mac, it's far, far less efficient. This is one of the reasons that a computer that runs Mac OS has to be bigger. It's far less efficient. So it needs more memory and everything. And then that stuff overlaps into other stuff, because in places where we don't necessarily have to have more memory, that Mac has more memory, so it's doing other stuff faster, but it has to be bigger for this part. It actually puts it on that line. So a straight line really is a straight line on a Mac. And well, obviously, like I pointed out, we can't turn on and off the space in between the pixels. All we can do is turn on and off the pixels. So it's usually going to look like this. but we don't necessarily have a guarantee, right? Maybe if we draw it and everything looks like straight lines on our system, when that gets opened on another computer, the other computer thinks this dot should be rounded over to this pixel. And that's really going to mess up our line then, right? Because then we have that big jagged spot in our line where it got rounded to the wrong pixel. So that's where the Macs are definitely better for graphics. Macs are definitely better for 2D graphics because of that right there. But that is far less efficient, which forces Macs to be bigger. And then on the things where that doesn't matter so much, Mac just has more memory and speed available so that it can do this. But that is the difference you'll hear in graphics. If you've ever heard people mention that and wondered about it. Let's see, and my notes here were so I don't get carried away. I'm going to write generalized 3D stuff. So we have what we store is data about vertex, edge, and face. Whoops, I probably should have made those plural because we're going to have more than one. But vertices, edges, and faces forming polygons. So a vertex is like a spot, a point in 3D space. So we'll have a couple points, X, Y, Z, and a couple more down here. I'll put little circles on them, little subscripts. So X naught, Y naught, Z naught, or 0. The little subscript there, if you can't read it, that's a 0, which is often pronounced not N-O-T, the negative, but the old English term, N-A-U-G-H-T, the old English term for 0. So X naught, Y naught, and Z naught. Then another point over here, X1, Y1, and Z1, and the 2's over here, X2, Y2, Z2. So 3 points in 3-dimensional space, and connecting those points, we have edges. So we have a vertex, and then connecting the vertices are edges, and then the space in between is the face. And we just do lots of this to represent a surface, forming polygons to represent a surface. And there's lots and lots of different types of this. But that's the general idea. We take points in 3D spaces and connect those points with edges, and then in between those edges, we fill it in and say that there's a solid face there. And that's how we represent 3-dimensional data, because then we can turn that around. And the next step beyond that gets into parametric modeling, where we add more data on top of it. We take that surface, which is just the outer shell, and then we start adding background data, like say, we could tell the computer, okay, this is made of 70-20 steel and has a rusty appearance, and then we can start doing accurate simulations on it with background data. But yeah, I wanted to look at a couple of these things. In particular, the other thing that goes with graphics, which I didn't have much to write on the board with. Step out of the way in case anybody was taking notes on that still. Oh, I'll erase that. That's not related to this. That's just the pronunciation. When you see a subscript 0, we use the old English term quite often. So when you hear people say like X naught or T naught, that's referring to the old English term for 0, or the old English term for nothing. I got distracted. Oh yeah, so now that we have images, well, a still image gets kind of boring, right? It's much more interesting when those images move. And I didn't have much to write on the board about this, but I wanted to look at some animation stuff. So leading into those animations, we'll look at some, we'll start with 3D vector graphics, and then we'll do the 2D vector graphics. And what I was going to show you for the 2D graphics would work on pings and GIFs and bitmaps as well, but it gets a little bit funny. It works much, much better with the vector graphics because then we're manipulating that equation. We're adding scale factors into an equation to move things around, which works a whole lot better than just taking that pixel data and trying to stretch or compress it in different groups or move it around. So it will work there, but it works a whole lot better with the scalable vector graphics. So let's look at that. And I want to end with the 2D thing because I think that's what will be most useful for you all. So I want to finish with that fresh on your mind. I'm going to go ahead and share my screen. I sent out an announcement earlier. Did you all see the announcement about the software I was going to use? There's 2 pieces of software I'm going to use. The first, both of them are open source. Oh, I sent out the links to the 2 pieces of software I was going to use in case you wanted to follow along. But it might be better to watch just to kind of listen and watch, and then this video is going to be posted in 10 minutes or so after we finish anyway. So then you can go back and watch the video to kind of practice some of the skills if you want to. But I just put a couple links. So 2 open source pieces of software for 2D things. I like this software called Inkscape, which we will look at in a few moments. It takes a minute to open though. I'm going to go ahead and hit open on that. And then for 3D software, a very, very popular one is this one called Blender. So I'll open that and it opens a lot quicker. And hopefully the other one's not going to slow us down doing stuff. But I can see the video is a little bit jumpy, so maybe I'll kind of stretch this out. But we want things to move, right? Still images get boring. So especially if you're talking about like that example I keep going back to of putting together a PowerPoint for describing a security breach to a client, right? You want things moving. You want you don't want to just put a still image there. You want to something in the image representing your data so that the client can see that data escaping where it needs to be and see and actually visualize the importance of it, which means we need movement. We need some animations. So first off in animations is the general topic here. So we're in 3D space. Right? With 2D stuff, we know we're going to be looking straight on. So we know that we're just drawing on that 2D surface. But with 3D space, we almost always need to include a camera. We have to set that up to say what angle we actually want to be looking at this stuff in. So that's going to be important. And a light. Where's our light source coming from? Where are the shadows falling? Where are reflections going to, and things like that. So that stuff's almost always included. But when I hit a new thing, it just started with this cube. I'm going to delete that and kind of add a new one in. So up here, there's a button that says add, and it's a surface. That's the technical term is going to be a mesh representing the surface, and I'll just add a cube in. So just 6 squares put together. Right, how many is that? 8 vertexes in space, and then we connect those with edges and fill in some space, some stuff to make a face to represent a cube. With that selected, if I come in edit mode, you can see all the different parts here. So there's those little dots at the corner. So I can select vertex by vertex. Oh, yeah. I brought my good mouse in, or not a good mouse. I brought a regular mouse in because the little touchpad does not work well with 3D stuff. Plug the mouse, and yeah, then I can like select all 4 of those vertexes, and you see those. Hopefully you can see that there's the edges in between those vertexes that I chose, and that face got selected. Or I can switch the selection method and choose a couple of edges here, and then the face that comes along with them. Or the selection method, I can just choose face by face. And then that's how we represent our data with different vertices in 3-dimensional space. Then we connect those vertexes, just connect the dots with edges and fill in the space in between them, color in the space in between them to make a nice surface that looks like a 3-dimensional thing. So for animations, I'm going to do something a little more interesting here and kind of express this point. I'm going to delete that cube. And then I'm going to go over to my GitHub page. Hopefully the browser's not going to take forever to open. And I have some stuff already made that'll hopefully look a little more interesting than just a cube. I'm going to go over to my GitHub page. GitHub is what's known as a repository. It's a place where we can store computer code, basically. So instead of saving it on our hard drive, there's special setups we have on servers so that we can store code on those servers. And then unlike other regular storage where we can always just store files online, then download them and use them, a repository is kind of a step above. It's specifically for storing code so that when we go to write another program, we can refer to that repository and we don't have to download the code and copy and paste it over to the new thing. We can just refer to where it's stored at. I have a bunch of things here out this one. So here's a bunch of starter shapes that I did, so I wouldn't have to go back to a cube every time. Well, I guess I should show that. So before doing this, let me add the cube back in. If we want to and then to make different shapes, I grabbed those edges, but I didn't do anything with them. Like we can grab that vertex and I'll click the little arrows here and move that vertex to a different spot, or move this one just over here, drag that one down, bring that one straight up, and kind of stretch those, stretch the vertexes to different places. You can add in new ones. What's a quick way to subdivide this? I select this face and hit rotate things, spin them, scale them up and down. Maybe I want to make that face really big. Come over here, grab this face, and I'll scale it down. I'll rotate that face around, spin it around, and just make different shapes. Use a knife. And we can kind of cut in new edges to get more vertexes to move around. And I have like another vertex here that I can take and drag off here, grab this one. And we just set up those vertices, vertexes and edges and move them around to the position we want. So obviously that can be a little time consuming. So instead of starting with a cube and doing that every time, I went ahead and set up some starting points. These are elephant, that'll work. I'll grab the first one here. So this thing, it just automatically starts with an elephant. I can't remember which one this is. I think this might be an African elephant. But I went through and did a bunch of research and got all the proper proportions and spent several days putting this together. So it still doesn't have the details in it. It's still just a starting point. But it's the starting point is proportioned correctly for an elephant. And I cleaned up extra vertices and set up faces so that like where the eyes are going to go, that's roughly marked. There's already a face position for it. There's just not the details of an eye there. And sort of good starting points, but this is how that data is stored. So these square brackets here, that means there's a collection of things. Actually, I'm getting ready to download this. So I'm going to download that. And then we'll look at it someplace I can highlight it. Uh-oh. Everything started going really slowly on me. There we go. Raw data. And I will just save this. Downloads, that'll work. That way I can close the browser because that's probably the thing slowing stuff down the most. So you'll notice on this software, there's a lot of buttons. Way over here on this tab, there's a tab for scripting, and I can just open up some code to run there. So if I go to my downloads folder now, wherever that's at. Okay, so here's that code we were just looking at, and hopefully with the browser closed, it's not going to go quite so slow. But there's this huge collection of points in three-dimensional space. So X, Y, Z value, and a word rapid, there's a lot of them there. Obviously a lot of points, but a whole lot of X, Y, Z values to make up all those points. And then down here, square brackets mean we have a collection of things. The first thing in that collection is a collection of points. So that defines the faces, and then I just left this code to automatically fill in the edges as needed. So we have that huge collection of vertices. So then we get down here and we'll go to the 178th item in that list. And then the second item in that list. And the 8th item in that list. Then the 356th item in that list. And the 180th item in that list, which is actually off by 1 because we start counting at 0, but it just seemed easier to say the numbers showing on the screen here. But it goes to those 5 vertexes and then fills them in with a face. And then the next item looks like it has another 5 vertexes. And one of them is that was also included in that first face. We can see they're connected there. And then over here, next thing is a face that connects 4 of those vertices. And it just builds up all of those. So now if I run this, if I come up here and run this script, and it ran, oh, whoops, I bet I did this. Oh, okay. I thought I downloaded a different one. I downloaded the one that adds the button, not the one that actually draws the button. So I ran this script, but I think I already had the button installed on here anyway. But that's the point of I have another version, which is exactly the same, except for what it does at the very last line. And I thought I'd downloaded that one. I guess this is a good example of that open source thing that we've talked about a couple times. this software didn't have a button that would automatically draw an elephant. So I wanted a button that would automatically draw an elephant. So I went in and manipulated that source code, which I believe I already had the button, so it probably didn't duplicate it. Hopefully it didn't duplicate it. That would be a unnecessary redundancy, but I manipulated the source code to add a button that draws an elephant. So I can just click this button and, well, actually only draws half an elephant, so I still have to do a little bit more. I'm gonna click this thing, a modifier, and then I can mirror everything on there. The thumbnails are in my way. I'll make a mirror, so because animals are symmetric, so I only drew one half of it, and then we can go in and add details on half of it, and then just automatically mirror it. So you can see it's a bunch of vertices formed and filled in with faces to form the rough shape of an elephant. So a starting point that is proportioned correctly, make it easier to start and fill in the details later. I can at least click this button though, shade smooth. So I'm going to get rid of all that jaggedness and get to the actual point of what I wanted to talk about. So marking a bunch of points in three-dimensional space and then filling in the space between them, you get a surface that kind of looks like an elephant. And you're probably familiar with like the old style animations, like what Walt Disney did, right? He drew a picture, and then he drew a picture that was slightly different, and then another one that was slightly different, and lots and lots and lots of pictures that were all just slightly different from each other. And then just played those in rapid succession, and it gives the illusion of movement. So we can do the same thing, but computers are great for the tedious busy work. So instead of doing every single picture, we can just set up like some start and end points, and then let the computer fill in all the space in between. Like, okay, we're going to start at this picture, we're going to end at this picture, and let the computer fill in everything in between. And it's still essentially the same idea of animation, just the computer does most of the work. But what we have to do is define what's going to be moving there. So the next step on the top of graphics is to add something that we can move around. In 3D software, and then we're going to look at the same thing in 2D software, we can add a skeleton to it, which has more, well, like a skeletal structure, as a rigid structure to it. Just like our skeletons, right? Without our skeletons, we would just be a pile of a mound of organic matter, almost like a puddle, right? The skeleton defines the structure and the movement, the position, and everything. So we can do that with our surfaces here. We can add in a bone, and I'm just going to do a couple really quick to kind of go over the key points. Let's see, I'm going to rotate that around the x-axis, and oh, I need to see that, so I have to turn something off. So with those bones, we can do a lot of different things. You can tell there's a lot of different buttons here. I'm click this one that says in front, so I can always see it. We just kind of position that. And if I come over here and go to edit mode, I can push the E button for extrude and make more bones. So I hit E and extrude something out to represent like the a bone for the skull. Is that centered? I should center that. Try to get that about centered. Okay, there we go. So like a bone representing the skull, and well, there's going to be a quick animation, so I'm just going to do a couple down the trunk here. Extrude that, and put a couple bones to represent that elephant's trunk and the actual structure of it. Maybe I'll do a leg as well. Extrude one out there. And we're in three-dimensional space, so we have to constantly move back and forth and define where to make sure things are in the right spot. And I'll do a couple bones for a leg. Oh, that did not go to the right spot. So move that over. And notice it's like those vertexes and edges and everything. Every part's separately, so we have to move all those separate parts around in three-dimensional space until we get the image we want. That'll work. But once we have a few things there, obviously you'd probably want more than just the trunk and one leg, but hopefully that'll get the point across. We'll come back, so we're looking at objects. And we have two objects. We have a skeleton and an elephant, and they're separate things. We need to tie them together. So I think I select this one first, then hold Shift and select that. Now push Control P. We want to make one of those objects the parent of the other one. So the very last thing I selected there is going to be the parent of the other object. So I selected the skin first, that surface that kind of looks like a starting point for an elephant. Then I selected a skeleton, and I'm just going to choose automatic here. Weighting is how much that skin deforms when a certain bone moves. Right? Like our skeletons, if I move my right elbow, the skin on my left ankle doesn't deform with it. Right? It's so we have to define what goes with what. The automatic's probably okay here. So if I select both of those, I have an option for weight painting. Here we can, add and remove different amounts. How it removes. Control. Nope. I can't remember which button removes it, and it looks like this. As I click on different bones, you can see where the skin attaches to it. And it looks like the wrong one's here. So Alt. Whoa, not that. Undo that. Not that click. Not that one. I'm drawing a blank on which button to undoes stuff. You can add stuff to it. Well, I'll just leave it like this. It's just a quick point. But we can click on different things and say this. We want, when this bone moves, we want this skin to stretch with it. And I can't seem to remember which one undoes that. I need to hold down both of them. Nope. Nope. Huh. Yeah, I can't remember which button does it. I haven't done it in a minute. So extra stuff's going to move here, but maybe the trunk will look better. Yeah, so looks like the trunk doesn't have extra legs. So like when this bone moves, that part of the skin right there, that color coding shows how much stretch, what part of the surface is going to stretch and deform with it. And then to do that, with our skeleton, we can just, we have this option for pose mode. We can just take that and maybe rotate that. You can see the skin just moves right along with the skeleton. Or if I select this one and rotate that, the skin kind of moves along with it. Then the legs got off somehow. It's selecting both of them, but the general point's still there. Right? If we grab the bone and move it back and forth, other stuff moves with it. I'm not sure why the, oh wait, I know why the stuff's doing that. I never applied the mirror modifier, did I? Oh, not selected now. This one, then this one. Oh, it's still going to do that. Yeah, it's doing that because I forgot to actually apply that mirror thing. I should have made that one whole piece before doing that. Undo that. One more, I think. Okay. So now I select that and turn that into one piece. Sorry, got a little distracted, but the stuff we saw. So we select the surface. Oh, the other way. Like, yeah, the surface and then the skeleton. When we hit Control P, we can set the skeleton as the parent to that. Then select the skeleton and then the surface. Okay, now it's only on one leg. So like this bone is only going to stretch that skin that's color coded there. Or this bone's only going to affect that skin. Looks like there was a little overlap, but it's not, I didn't accidentally leave it symmetric that time. And then we can select our skeleton and pose it into different positions. So if I rotate this leg, you can do things. But we probably want that to happen repeatedly. So to repeat the things, we set up what are called keyframes. Let me zoom in here. So I'm going to select all those bones, and then right click and hit Insert Keyframe for location, rotation, and scale. So everything's locked in place there. That's the key point, is the like time, the frames play forward and loop around and around and around. Every time it gets back to frame number one, things have to be in that position. So I'll come over to like frame 20. And again, up here in this little image, right click and insert a keyframe. So like this is an important one for location, rotation, and scale. So that frame 1 and frame 20, the skeleton's locked in that position. And then somewhere in the middle, I clicked right in the middle on frame 10, I'm going to make some changes. So maybe on frame 10, I'm going to rotate this around the x-axis. And I'll do that for all the trunklets. Rotate that. Rotate around the x-axis. Same thing with leg. Rotate that forward. Rotate that one back a little. That'll probably work. And then here at this frame halfway in between that start and end point I set, I'll right click and insert another keyframe and say, at this frame, as it plays, I want the bones in this position. And then the computer can fill in all those gaps in between. So if we jump back to frame 1, and then down here, start and end, I'll set the end to like 20. I know this is going very, very quickly. It's something you want to play around with. It gets a little complicated. Whoops. Reselect that. But we just define where, as far as where and when we want the bones. So at each particular time frame, what position do we want the bones in? Then when we play it, the computer fills in the gaps and we get some nice smooth movement. Then over here, that's what the cameras, we can see what the camera's looking at. So we didn't even catch the whole thing, but it makes animations a lot easier. So we get our surface, put together our surface, then give it a skeletal structure, and then we link those together and define the movement of that skeletal structure. And the skin just kind of comes along with it. And we can also do this with 2D stuff. That was the other thing I wanted to look at. So this will go very quickly. I'm just going to draw a quick picture here and look at difference in scalable vector graphics. So I'm going to guess that most people have seen graphic software before, right? At least the basic ones like Microsoft Paint and things like that, where we just draw some colors on there and get an image. This interface allows us to do a similar thing. This is some software called Inkscape. It's for drawing scalable vector graphics, though. So unlike Microsoft Paint, the images we draw here, we can scale up or down or to any size we want because of how it's stored. So I'm going to draw a big box here and maybe make that blue. Then I'll draw a box down here and make that green. Try to roughly do the image that I kept drawing on the board. I'll put a little circle here, make that yellow. Then a tree thingy. Put a green circle and a brown box. And if you're used to just some basic drawing software, once you get the colors on there, it's set. But notice I can still select each piece independently. So I can select the background and move that around. Or select the tree trunk here. Whoops, an extra shape showed up there. Select the tree trunk here and move it back and forth around, or it looks like it's at the wrong layer, so I could lower that so it's behind the other stuff. And all the shapes are still accessible. And that's because of how we save this data. So just a quick image, just the interface should look somewhat familiar. We have brushes and pens and pencils and things to draw colors on there. But unlike some of the basic ones, all our stuff is still independent. It's still a bunch of separate things held together. And we can stretch it up, change the size of it, move it around, and deal with all the parts separately because of how we save it. When I go to File and Save, I'll just stick this in my delete folder. Sure, call it drawing, but notice the type is the SVG, the Scalable Vector Graphics. Now, if I go to open that, come over to File Explorer, I just come over here and try to open that in the delete folder. Well, it's got the Inkscape thing, so I'm going to go to Open With and just open it with the text editor. And you'll see that it's not arbitrary computer data that we can't hardly make sense of. Right? Everything is written in a human readable form. In particular, it should look somewhat familiar from that assignment a couple of weeks ago where we made web pages with HTML. It is scalable vector graphics are stored as a markup language. So that ML at the end as well, just like we have on HTML. It's like a really nice on web pages, but it's all human readable data. So internal data there, and you can see the SVG tag, just like we saw in the HTML, we have those angle brackets, and then the type of thing we have is going to start here, and then way down at the bottom, here's where it ends. And everything in between there is scalable vector graphics. Then we have some other stuff. So like here is a rectangle. We have this rectangle filled in with no red, 80 for the green, and no blue. So that must be the rectangle at the bottom. Or here, an ellipse, something circular that's filled in with lots of red, lots of green, and no blue. So an even mix of red and green gives us yellow. So that must be the little sun from the image. In human readable form, we can alter it in the text editor here if we wanted to and do different things with it, but everything is still separate in pieces, so we can adjust it really easy. Make any adjustments we want, such as animate some things there, doing essentially the same thing we did in Blender. So that, or essentially the same thing we just did for 3D stuff. I still do this in Blender. So I'll come back to just the basic layout and I'll just delete this. Oops. Well, I'll make a new one. I'll new. I don't need to save that. So instead of making a three-dimensional shape, though, I'd like to use those skeletal animations on that image I just drew. So I can import other image types. I'll go to File, Import. One of the options is Scalable Vector Graphics. So I can bring in that thing I just drew, wherever that was. I think it's here, yeah. Oh, it's really small. So it's a 2D thing, so I'm gonna adjust and look from the top. Maybe move this over here and scale that up bigger so that it's not so small. So it's not quite so small of an image, but well, I should have pointed this out before. I'll add a cube somewhere in here. Notice with the cube, we have this little symbol here that shows things fully connected, like it's forming a shape. But with those things that I just brought in, they're open. It just says they're curves. So I do need to convert those to shapes in order to do that. So if you use like Inkscape and put together a quick SVG graphics, throw some stuff together, and then import it into something like Blender, and under Object, there's an option of Convert to a Mesh, which is a surface like what we were seeing before. So I'm just going to go through these all these curves that were imported, and convert those to a mesh. Object, convert to a mesh. The next little path here, object, convert that to a mesh. Object, convert to a mesh. You can see it didn't take long with just a couple things, a quick picture like that. But obviously, as you get more detailed, it'll add in more and more details. It can be a little time consuming at points, but hopefully the general idea here is going to make sense. So we go something like Inkscape and draw up some SVG graphics. So we have scalable vector graphics that we can stretch and move, and everything's treated independently. And then I brought it into Blender and just converted that to a mesh, to the surface like we would normally use in 3D graphics. And something I like to do, just because I think it makes it a lot easier to animate, is notice it is still a flat surface, but we're in 3D software, so I can like grab these things and put them on different levels. So like there's the sun, so I could bring that up so that it's in front of the other stuff, and there's not any overlap, because if we're looking at it straight on, we can't really tell anyway. And like that ground, I'll bring that up a little to a different level. The tree has several parts, so I'll just move this one down. So now all the parts of that image are at a different level, and I can treat each one independently. Well, maybe this one needs to come up a little. There we go. So they're all, if we look at it from the side, we can see it's a bunch of different levels. If we look at it straight, this button, if we look at it straight on, it's still that 2D image. And then we can add that skeletal structure and animate it the same way. If I come to add and add in an armature, just add in a bone. Really want that to lay flat. Rotate around the y-axis, something like that. Maybe move it this way. And scale it up a little. That'll probably work. I'll stick it like here. Oh, once again, I have to come over here and click the button hidden way deep on the little armature options, and then the viewport. As you can probably tell, I've spent a lot of time with software like this. I find it very fun, but there's a lot of buttons, so it does take a good bit of time to learn all the buttons. So as you're learning it, there's a lot of going to Google and like that one I just did, how to see a bone in Blender, and doing a lot of things like that. Well, you can see there's a lot of buttons here. But then, just like before, once we have one bone added, you can come over here and switch to edit mode, and then add other bones. So I'm going to hit E to extrude, and I'll just come over to that point, and then I'll come up here and make a bone for that tree. Or here, I'll come to that first knob, extrude up a little, extrude another one to be a bone that kind of represents the sun. I'm going to look at them from the side and position them. Once we get to the final result, we'd turn the visibility off and wouldn't be able to see those bones anyway. And then I'll position these so that they are next to those meshes that I want to move. There we go. So now there's some skeletal, basically skeletal structures. Armature might make more sense here. There's armatures that those parts of the shape can interact with. Oh, I guess there's one more step here. On the object, I turned all those curves into meshes, but they're separate. They're not a single shape. So I do have to select all of them, which I'll just do over here. So I'll select all those shapes and hit Control J. So now it is just one shape. And select the armature and hit Control P. Hopefully automatic weights will work. To make the armature the parent of that shape. Here's you can check it the same way. So select the armature and then the shapes and check weight paint. So you can see if this bone moves, it looks like the stuff here is going to warp and deform. Or if this bone moves, it looks like just that circle representing the sun's going to move. So it makes it really easy to animate those parts. That'll probably work. Probably spend a little time refining that better, but if I come over to the animation tab, that's not a good view on that. It's where I can see it. Once again, the most important part is we have to set up our keyframes to define the important parts in our animation. So here at the beginning, I'm going to switch this to pose mode. So select the armature and go to pose mode, and right click and insert a keyframe for location, rotation, and scale. Whoops. Select all of them. I just pushed A to select all of them. And now with them selected, I'll insert a keyframe so that it's locked in position there at the beginning. I don't know, somewhere over here, I guess frame 30, I'll do the same thing. That way it can loop and get back to the same thing. So right click and insert a keyframe so that they're locked in position there. Um, 30 frames, so halfway in between them. That looks like halfway. Sort of a traditional animation thing is like the sun going down and coming up to represent time passing, right? I'll just do that. So to represent that, I'm going to take this bone, and because it's connected to the one actually controlling the sun, and I'll scale that down to really small, so that it's like the sun goes down. And once again, hit A to select all of them, and insert a keyframe. So halfway through, I want that stuff to be in that position. I'll come back over here somewhere and do the same thing for like the tree waving in the wind. I'll just rotate that a little bit to the left, hit A to select all, insert a keyframe, and then lock that location, rotation, and scale in. And then somewhere over here, I'll do the same thing. I'll grab this armature controlling the tree, R to rotate it a little bit to the right, select everything, and insert a keyframe to lock that position in. And then the computer fills in all the gaps in between. So I know that was a lot very quickly, but hopefully you saw there how easy it is to grab a 2D animation and animate it. We just do the, what was that, about 10 minutes there to quickly throw together some SVG graphics, import them into Blender, turn them into a mesh. Then we can add an armature to it and set up the position for the armature, and the computer will fill in all the spots in between. Then we have sort of an animation. Oh, whoops. I'm ending at the wrong point. Should probably go all the way to 30. We have that animation of the sun going down and coming up, and the tree like waving in the wind or something. I know it was a very, very quick pass there, but hopefully you can see that it is very, very easy to do that. It is not complicated, just takes a little bit of clicking around. So the two softwares I used to do that were Inkscape to do the SVG graphics and Blender to add armatures to it. And I made it a point to do that one last because I think that one will be very useful for you all. Right? 2D animations, that's what we want to throw in a PowerPoint so that we can express something clearly to a client. So you can see it's very easy to put those together. Obviously, they get much, much better as we put a little bit of time into it. But definitely something to play around with. And those two pieces of software are my recommendation for that. This video will be up in about 10 minutes or so. If you want to mess around with that at lab time and have any questions, let me know. Because this is an active subject. We learn by doing. So the thing I did at the end there is going to be my recommendation on something to practice, because doing quick 2D animation is something that will probably be beneficial for you. Right? Both people here have expressed interest in security stuff, and the person that I know will watch this when he gets off work later tonight is interested in hardware stuff. So that means you're going to be explaining things to clients that aren't going to know the technical terms. So having a nice animation in a PowerPoint can make a big difference there. So that's how you kind of put those together. Oh, I guess one more button that I can't really click here because it's going to make everything slow down. Once you get everything set up, then there's this button up here at the top. It says render, and you can just render down the animation, which takes a long time. I'm not even going to click it on the Zoom call. It takes a long time when not on a Zoom call, and then that'll give you all the images, kind of like the Walt Disney thing, right? Where there's 50 different images. It'll put them in order so that you can rebuild that animation anywhere. But very easy to do. That would be my recommendation to practice. This video will be in about 10 minutes, so you can reference that. But a useful skill, but as always, it's an active subject. We learn by doing. So I want to make sure there's plenty of time. Looks like we got a little over an hour left on our scheduled time to do stuff and learn computers. You don't necessarily have to do that, but I did want to make a quick pass of graphics because in most of your classes, that's going to be skimmed over, right? The most you're going to get is a quick comment that graphics are something that exists. So I wanted to talk about those a little and different types we have. And then that last thing we did there, scalable vector graphics with armature animations are very quick, very easy. Y'all saw me do that in 10 minutes while explaining the process. So it's very quick, very easy, and will be very useful for you. So that would be my recommendation to practice. But as always, this is our time to learn IT. So please spend the next hour and 5 minutes learning IT stuff. I will be sitting here ready to address questions if you have them. Text messages and Ivy Learn messages make noise on my phone. And yeah, whatever you feel like working on. If you have a question, send it my way. Otherwise, I will see you all on Thursday. Everybody have a good night.